Okay, so today we're going to prove the edge group theorem, which remember is this isomorphism of groups. And so to start, I want to continue where we ended off last time with the simplicial approximation theorem and more specifically subdivision. So subdivision is a process which takes input a simplicial complex, K, and outputs a complex that we'll write K1 with two key properties. The geometric realization of K1 is the geometric realization of K, or they're topologically equivalent. And K prime has smaller simplices, or I guess it's geometric realization. So to illustrate, in the case of a one simplex, this is a simplex-wise procedure. So it's a procedure that you apply to simplices individually. You apply it to each simplex in a simplicial complex, and you get a new complex. If you just start with this one simplex, then the subdivision process outputs, you just divide this edge in two. A little more interesting example, if K is equal to just a triangle, two simplex, then, so let me actually label these here. So here's K, here's K1. And so in this case, if K is this triangle filled in, then K1 is, it's the same triangle. I should draw it sort of the same shape and size, but then we subdivide it like this. So, well, it's a simplex-wise procedure. So the edges are going to be divided as before, and there's going to be one additional vertex in the center, and well, there are these edges. I'm telling you how this procedure works in these particular examples before going through the general construction. So this is how it looks. Right, so to formalize this procedure, here K has simplices well, so let's label these vertices 1, 2, 3. Remember, simplex, it's a subset of the vertices. So there's the vertices, the one element subsets. There's edges, 1, 2, 1, 3, 2, 3. We'll write them like that. And then there's a single face, so two simplex, 1, 2, 3, whose vertices are 1, 2, 3. And so K1 is going to have vertices. So in general, K1, okay, so I guess I'm giving a definition of K1 now. You should keep this specific example in mind as we go through it. So K1 has vertices V sigma for sigma, a simplex of K. So there's one vertex for every simplex. So for example, in this case, we have 7 simplices, and there are 7 vertices here. So there are the original vertices, and then there's a vertex 1, 2, 2, 3, and 1, 3. And then there's in the center a vertex 1, 2, 3 for the face spanned by 1, 2, and 3. And okay, so those are the simplices of the subdivision, and the are the vertices. Now I need to say, what about higher dimensional simplices? So if sigma naught up to sigma n are simplices of K, then, and sorry, not then, there's one, and they're nested, so sigma naught is contained in sigma 1, and so on. Then this collection V sigma naught up to V sigma n, this is a simplex of K prime. Okay, so you have to remember simplicial complex, you have a vertex set, and then simplices are subsets of the vertices. So K prime has vertex set, these symbols V sigma, one for each simplex of K. And then I'm telling you when n plus one of these span an n-dimensional simplex, precisely when you can arrange them in this nesting order. So for example, in this picture, you have 1 and 1, 2. So you have, so e.g. Above, there's, well, V1, V1, 2. That's an edge here. This is in K1. You also have like triangles V1, V1, 2, V1, 2, 3. That's like this triangle here. But you don't have, for example, I don't know, V1, V2, 3. So the vertex 1 and the vertex 2, 3 are not connected by an edge because, well, the simplex, yeah, I mean, the vertex 1 is not contained in the simplex span by 2, 3. Okay, so this is the recipe for barycentric subdivision of a simplex. And yeah, okay, so I guess this wasn't in general. This is for K, a simplex. And then in general, you do this procedure. Or so in general, I mean for general K. You do this procedure on each simplex. So, okay, so a picture. You start with this complex, say these triangles are filled in, and then you get a new complex with more vertices. Well, you just subdivide each thing individually. So let's see, so now we have a vertex here, you divide the edges, and then you divide the faces as well. And you have a vertex in the center of each face. Okay, so this is how this works. Okay, so this procedure is the barycentric subdivision. There's different sorts of subdivision possible. There's different ways to subdivide simplices, but this is the barycentric way to do it. And it's called the barycentric subdivision for the following reason. So let's consider the geometric realization so let's fix K. So its geometric realization is a subset of Euclidean space. And well, the simplex, so for sigma, a simplex of K, the geometric realization, let's say sigma is with vertices V naught up to Vn, then the geometric realization of sigma, this is the simplex spanned by V naught and Vn and Rn. So you have to remember how we constructed this geometric realization. We chose a injection from the vertex set into Rn, and then you look at all the simplices spanned for them for each simplex of K. So the barycenter of this sigma is defined as, so V sigma is 1 over n plus 1 times the sum of V naught up to Vn. So for example, if there's just two vertices, then this barycenter, so V naught V1, well, you could write this as expression as V naught plus 1/2 V1 minus V naught. Okay, so it's the vector V naught plus 1/2, V naught plus 1/2 V1 minus V naught is this point, and you get exactly the midpoint of the edge. And in general, for a simplex, you get some point in the center. That's the barycenter of the simplex. And okay, so one thing to observe then is, well, if you choose V sigma, so let's see, you're right. So we choose K1, so let me say it this way. So to realize, or to obtain the geometric realization of K prime in Rn, we can choose let me say it this way. Given the realization of K in Rn, we can choose, so here we have the vertices V naught up to Vn. These are points in Rn. We can choose V sigma choose for V sigma in K1 vertex. V sigma to be 1 over n plus 1, this barycenter. And then what we find that K1 is actually equal to K as subsets of Rn. Okay, so I have a feeling this is I'm potentially being confusing here. So, okay, so you have to remember, simplicial complex, it's just this abstract thing. We have a vertex set and a collection of subsets of it. And this geometric realization, you first map the vertices into Rn, you choose the vertices in Rn in general position, and then you fill in the corresponding simplices. But that requires a choice of choosing vertices in Rn. So I'm saying you can choose the vertices of the subdivision to be these barycenters. And now I see this is a typo. This should be plus. And if you do it in that way, of course, there are other ways to choose how the vertices of the subdivision map in. But if you choose them to be these barycenters, then the subdivision and the original simplicial complex have the exact same geometric realization. Okay, and I guess this is kind of what is suggested by these pictures that I'm drawing. But okay, so this is an argument for why this subdivision process satisfies this condition. The geometric realization of this subdivision is topologically equivalent to the original, and in fact, it's equal as subsets of Rn if you with the proper definition. Okay, sorry. So I hope that's not too confusing. So now, right, so let me mention that, so note that subdivision can be iterated. Anything you can do once, you can do twice. So, so if you start with, maybe I should switch to drawing lines. This might be nicer. Let me try drawing this as lines. So you start with a single triangle. Whoops. My pen is being a little slow. And then we divide it once. And then each of these triangles we can divide. So let's see. And yeah, I mean, we could just divide each of these triangles again. And we get some sort of picture like this. And right, so this procedure of, sorry, let me just draw this whole picture. I know this is kind of slow. I hope you're watching this at twice speed. Or just fast forward. Okay, if I did this, I guess it's kind of a nice picture. Right, so we'll write K R for the rth iterate of subdivision. Okay, so this is like K2. You start with a single simplex, you divide it once, and then you divide it again. And the main thing to notice is, yeah, I mean, the diameters of the simplices are getting smaller. That's an important property of this subdivision. Okay. So now the main theorem that I stated at the end of last time, which uses this subdivision, is that so if you start with any map between simplicial complexes, I'm going to write this the other way. Let's say L to K, any map. Then there exists some R large, so that the induced map from the subdivision, the rth subdivision of L to K has a simplicial approximation. So remember, that's like a simplicial map S with the property that S of X is in the carrier of F of X for every X. Right, and so for example, last time we looked at a map, we looked at F of X is X squared, where here you view K, the interval as the geometric realization of K and L, where K are these two simplicial complexes. It's K, here's L, or I guess maybe I'm drawing the geometric realization. And well, we showed that F has no simplicial approximation. But if I subdivide O and I switched K and L, I want to remember to make L the domain for what's coming next. So let me just go ahead and do that now. It's not so important for this example, but if we subdivide, so I'm going to leave this to you as an exercise. So the exercise is that the original map doesn't have a simplicial approximation. If you subdivide once, it still doesn't have a simplicial approximation. But if you subdivide twice, then it does. Okay, so this is a good example to think about. Okay, so the simplicial approximation theorem, this is a technical result, and I think for the sake of time, we're not going to prove it in the course. We're actually kind of running out of time. There aren't that many lectures left, and I want to make sure we get to some good things at the end. And so, yeah, so we won't prove this, but what I want to do now is to show you how it's useful in proving the edge group theorem. My pen is still being kind of slow. So remember, this theorem says that for K, a simplicial complex, the fundamental group of the geometric realization is isomorphic to the edge group. Okay, so we've used this theorem and referred to it a lot at this point, but now we can discuss the proof. And the proof is not bad if you know the simplicial approximation theorem. So we're first going to define a homomorphism in one direction from the edge group to the fundamental group. So what does this do? So an element here, remember, is an edge loop. It looks something like it's a sequence of vertices. And what we send this to is, well, so we're supposed to send this to an element in the fundamental group, which is a homotopy class of map like this. And well, what we do is, let me just write it in words. We send this to the loop that piecewise, which is piecewise linear and traverses the edge loop. So, I mean, a picture, so say we have like this complex. Where all of these has these two-dimensional simplices, and there's this hole in the center. And well, okay, I mean, I'm just saying that if you have a loop based, or a sequence of edges like this is an edge loop. You can parameterize this as a path. Just do it in a linear way. It doesn't really matter how you parameterize it, but that's a straightforward thing you can do. And moreover, phi is a homomorphism, which is not hard to see, because if you concatenate two edge loops, then that corresponds to concatenating the corresponding paths. All right, so now what we want to do is show that phi is group isomorphism. We want to show surjectivity and injectivity. So let's start with surjectivity. So let's fix a homotopy class F in the fundamental group. So what we need to do is we need to find an edge. So we want to show, well, yeah, so let me draw a picture again. The same picture to illustrate what we have to do. So now what we're given is just some loop. It doesn't respect the simplicial structure at all. So this is our F. And what we'd like to do is show we can homotope F to be, to a simplicial map. So in particular, if we homotope F to a simplicial map will send, so it's a simplicial map from the interval with some simplicial complex, or with some decomposition into edges, into this simplicial complex. So it'll send, so if we do that, that means there's this simplicial map, there's some simplicial structure on the interval. So decomposing this into subintervals, so that this map on each edge, it sends it to either a vertex or an edge, and it does so in a linear way. So in that way, we obtain an edge loop, just a sequence of edges or vertices that we traverse, which would be the images of these vertices here. Okay. So let's set L to be this simplicial complex with geometric realization of L being the interval 0 to 1. So we can apply simplicial approximation to F, which is a map like this. So let me just say it this way. So there exists R so that this map F from L to K, R, has a simplicial approximation. And as we showed last time, so from last time we know S is homotopic to F. And so this does exactly what we want. After dividing, F is homotopic to this simplicial map, and that simplicial map gives us an edge path, which that gives us an element in the edge group, which maps to F. Okay, so this is how it works. One thing you might worry about is that the homotopy needs to fix the base point. So note that S of 0 is and S of 1 are both equal to P because F sends the vertex to a vertex. So in our discussion of simplicial approximations last time, we saw that if F of some point is a vertex, then S of that same point also has to be the same vertex. That's one property simplicial approximations have. So since F sends 0 and 1 to the base point, so does S. And moreover, under the homotopy is a straight line homotopy. So if F is equal to S on some point, then that's true throughout the homotopy. So this is a homotopy through based loops. Okay. All right, so now what remains is to show that phi is injective. So let's fix an edge loop. Let's call it epsilon. So let's write it P, U1, U, N, P. And suppose phi of epsilon is 1. So the identity element, which is, I guess you could write it as the constant path P. So this is in pi 1 of the geometric realization. Yeah, so that is to say phi of epsilon is homotopic to a constant. So that means, right, right, and I guess I'm being a little sloppy when I write this. You should map the edge loop to the homotopy class of this, since pi 1 is homotopy classes. So I'm going to think of, well, okay. Yeah, I'm maybe going to be a little sloppy in distinguishing between homotopy classes and an actual map. Yeah, so sorry, I do want to just be a little bit careful. So as before, so phi of epsilon, this is the homotopy class of F, and let's suppose that's equal to P. So that is to say, there exists a homotopy, which I'm going to write like this, H. So it's a map from the square into K. And it's a homotopy between F and the constant map. Okay, and so now let's consider L, which will be a simplicial. So ultimately what we want to show is that this edge loop is equivalent to the constant loop. Okay, so remember we have these, the edge group is edge loops up to equivalence. So to show the map is injective, we want to show that this loop is actually the trivial loop. So it's equivalent under these simple operations on edge loops like backtracking, pushing across a triangle to the constant loop. And we're going to do this by applying simplicial approximation. So now we consider L, so it's going to be a simplicial structure on the square. Yeah, so the thing is, so recall that the way we defined F, it traverses, there are these points along F which map to vertices. Map to the vertices, I mean, P, so it starts with P, this maps to P, this also maps to P, and this maps to like U1, U2, and so on. So we have these points here. And so there are these distinguished points along this bottom edge, the ones that map to the vertices along the edge path. And yeah, so if you're confused, well, there might be multiple reasons, but remember that this picture, I'm labeling parts of this square with where they map to in K. So everything here maps to P, and then along this edge, you map to this point maps to P, this point maps to U1, and so on. And then between you interpolate along an edge. Okay, so I'm going to put a simplicial structure on L by just making all of these triangles. So here, these were the things that map to the vertices. So I make these triangles like this. And then, well, so H, I view it as a map from L to R, or to K. And again, we can apply simplicial approximation. To say that H viewed as a map from the rth subdivision of L, this has a simplicial approximation S for some R, which says that i.e. Up to homotopy, we could say H, well, yeah, I'm just going to keep writing it H like this and say this map is simplicial. So let me explain what this does for us. So let me draw this picture again, and let me maybe make it simpler. Right, so after subdividing, so maybe we have to subdivide, let's just say we have to subdivide once before this map becomes, has a simplicial approximation. But what you notice is that, well, this bottom edge, so first observe that the bottom edge is equivalent in the edge group of the square to this composition of the other three edges. So the edge paths okay, so these they go through some edges here. These edge paths, let's say the green and yellow edge paths are equivalent in L with this subdivision. So then, since H is simplicial, which we can assume up to homotopy, then H of the green is, and H of the yellow are equivalent. Edge loops, right? So I mean, this equivalence, remember, I mean, well, okay, you have to remember how this equivalence was defined. I mean, it says that like this green path is also equivalent to the path that starts along the green and then goes over here and then is like this, because you have this triangle here. But then if you apply a simplicial map, the triangle gets mapped to something that's a simplex, either a triangle or something lower dimensional. And so then you also have, if this triangle gets mapped to a triangle in K, then you can do the same move in K. Okay, so this maybe is something to think about. So the images are also going to be equivalent just by doing the same sequence of equivalences. So then, and this uses the fact that H is simplicial. But so H of green, this is F, and H of yellow, this is just doing P. I mean, it does, all of this is P. So this is the constant edge path that just like does P, 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 but that's equivalent to just doing P once. And so this exactly does what we want. This shows that F is equivalent in the sense of the edge group to this constant loop. So that's the proof. All right. So I think we'll stop there. Like I said, there's not that many lectures left. So there's one more week before Thanksgiving. And so the plan is next week to start talking about something different. So the classification of surfaces, which is an important theorem. I guess it's come up a little bit. So we'll do that next time.